All right, thank you very much for the invitation to be here, and thank you so much for coming to the talk. So this is going to be essentially applications of oriented matroids. Behind this, there are a lot of oriented matroids, but this is a problem mostly in discrete geometry. This is joint work with, oops, doesn't work. Okay, Timothy Hogan, Deborah Oliveros, and Dominic Yang. So what's the, oh, there you are. So here's the quick overview of what I'm going to do. First, I'm going to tell you what Tverberg's theorem is, in case you have never heard of it. I'll try to tell you what that is. The general philosophy here is going to be very Ramsey. Good things happen when there's a lot of elements. I will present then the results that we have, and if I have time, I will tell you a little bit about the ingredients. Hopefully, that's a lot more matroids, so that's probably my goal. So as I said, in principle, the type of theorems that I'm going to present to you have to tell you that if you have a lot of elements on a system or a structure, you suddenly have organization. Something appears suddenly. And certainly the most famous theorem of this type is Ramsey, that has to do with colorings of complete graphs. So you know that when you have a sufficiently large complete graph and you color, suddenly there are monochromatic cliques. There's another theorem in geometry that maybe is also very, very famous because apparently this is the first paper by Paul Erdős in combinatorics. Before that, he only wrote papers in number theory. So this is the theorem that he proved that if you have sufficiently many points in the plane, in general position, necessarily there will be a k-gon. So there's a certain constant that depends on k, and that will guarantee you, for example, that you have a hexagon after a certain number of points. This is the Erdős-Sekeres theorem. Right? So this is the philosophy here. A lot of points, suddenly something happens. I want to talk to you today about another such theorem. And this theorem, in some version, was first proved by Radon in the 1920s, and then Tverberg in the 1960s. And this theorem essentially says that if you have sufficiently many points in RD, you can always partition those points in color classes, so to speak, that are very, very nicely behaved. So what is the theorem? Let me start with the simplest version, which is Radon's theorem. And I start with this version because it's perhaps more well known in the matroid community. So the theorem says you have a set of points and sufficiently many. In fact, in this case, we know exactly the number. If you have at least d plus 2 points, where d is the dimension, then you can always partition the points into two sets, the blue set, the red set, such that the convex halves of these sets intersect. And here are some examples. So in the plane, oh, I forgot this. In the plane, if you have 4 points, there's the, okay, in this case, green points and the red points, the convex halves of the green and the convex hull of the red intersect, and you can see these two situations. It's essentially the fact that when you have d plus 2 points, there must be a circuit in the matroid, right? In this type of matroid. So that's Radon's theorem. And what Tverberg did in the 1960s, essentially 50 years, more than 50 years ago now, is that if you have sufficiently many points, and I'll tell you what sufficient is in a moment, when you have sufficiently many points, there will be a constant that depends on m and d, that once you surpass that number of points, you can partition the set of points into m colors. You have m colors, and these colors, you consider the convex halves, and they must intersect. So for example, here, if you have m is equal to 3, I want 3 parts, and I'm in dimension 2, 7 suffices. So if I have 7 or more points in the plane, no matter how you give them to me, I will be able to partition into 3 colors, the green, the red, and the blue, such that the convex hull of these points, of these colors intersect. Is the theorem clear? Because if you don't understand this, you will not understand the rest of my talk. Yeah? Is it clear? Everybody is happy? Okay, so this is Tverberg's theorem, and it's classical, and it has been studied in so many different variations, and I'm interested in another variation of this theorem. Okay, so that's going to be the object of my talk. By the way, okay, so here the constant is if, so I said M, sorry, here in my slide, R is the number of parts. So if you have, you want to partition into M parts or M colors, or sorry, R colors, so you have to use at least D plus 1 times R minus 1 plus 1 points, and at that moment, the coloring will be possible, the partitioning will be possible. Are you with me? Okay, so that theorem is what I want to guarantee. Now, I want to study Tverberg's theorem from a different angle, and the angle is, I'm going to look at partitions. If I start partitioning the points just kind of any way I want, I will get a topological information of the partition. And this is something that topologists are very familiar with. It's called the nerve. So what's the nerve? When I have a family of convex sets, I define the nerve of the family to be the simplicial complex that I get. So the faces correspond to subsets. So I have essentially my simplicial complex is abstract simplicial complex. I label the sets 1, 2, 3, 4, all the sets, and the faces will be given by subsets of intersecting faces. Here's an example. So I made them by colors again. So here is, as you can see, there's the blue set, the red set, etc. And they intersect in this pattern, as you're seeing. But the pattern is collected here. For example, the blue, you can see the blue triangle intersects the orange, the green, and the red. So that means that, yes, the blue point is connected to the orange point, to the green point, to the red point. And in general, it can be more complicated, of course, right? For example, if I have 3 triangles that intersect on a point, so say, let's make it like this. So I have 3 segments that have a point in common. Well, the corresponding simplicial complex, the nerve of this will be a triangle, right? Are you with me, everybody? Questions? So that's a very important concept, the nerve. So now, clearly, the nerve depends on the partition, right? So the nerve depends on the partition. So if I have a particular set of points, so Jim gave me his favorite set of points, I start doing partitions, all partitions. I'm just starting to look at partitions. Every time I do a partition, I get a different simplicial complex, right? For example, here, I start with that set of points. That's the set of points that you gave me for Christmas. And in the first simplicial complex is empty, right, essentially. But then, in the second simplicial complex, I start getting something more interesting, right? Eventually, what do I get here? Here is a partition where the blue point, the corresponding blue point, is going to be connected to essentially 4 other points, right? So it's going to be actually a tree like this. This is the nerve. This is the nerve of that partition. I hope the concept is super clear now, because I'm about to tell you more about this concept. All right. So that's essentially my question here. I give you a set of points, and I let all possible partitions run. What simplicial complexes can I get as I let the different partitions run over my set of points? And I'm particularly interested in the situation when I have a lot of points. Yeah? Because as you saw in Tverberg's theorem, when I have a lot of points, good things happen. But one has to be careful. So this is a particularly interesting example to me. I wanted to share this example with you. Here is a particular, very specific set of points in the plane. I'm giving you the coordinates. I'm giving you explicit coordinates for 8 points in the plane. If I made a picture of these points, they look something like, the points look like this, like you see them in the picture. And there's no way, it's impossible to partition these points in such a way that the nerve, the simplicial complex you get induced from the partitions is that path, is that tree that you see there, the four length path. It's impossible. But if you add one more point, if you give me any point configuration with 9 points, any of them, I will be able to get the fourth path. That's the point. So this is the kind of theorem that I'm looking for. It's a Tverberg type situation, but for different nerve, for different simplicial complex. Is the aim clear? Okay, so for example, Tverberg's theorem, let me rephrase Tverberg's theorem. What Tverberg's theorem is saying is that if you have m colors, yeah, the m-1 simplex is going to arise as the nerve of some partition of any point set as long as you have sufficiently many points. I want to prove the same type of theorem, but for other simplicial complexes, not for simplices. Is the goal clear? Okay. So let me introduce a definition then. I'm going to say that a simplicial complex is the Tverberg if, again, there is a moment, there's a constant, such that if you have more than that many points, you can guarantee to me that there will be a partition, that gives me that simplicial complex as a nerve. That's the definition of Tverberg complex. In particular, obviously, what Tverberg's theorem says, what Tverberg's theorem is saying is that the m-1 dimensional simplex for every m is Tverberg. Are you with me? All right. So here is the question that my talk is going to answer. Well, not completely, but at least it's going to give you the first some results. Which simplicial d-dimensional complexes are the Tverberg complexes? That's the question. Yeah? So, and I'm going to tell you some results about this. So the first result is that not all simplicial complexes are the Tverberg, and here is my first interesting example, I think. So this graph is a one-dimensional complex. It's a one-dimensional complex. I'm giving you a particular graph. And this is not 2 Tverberg. So what I'm saying here is that there will always, no matter how many points you have, you can find a particular way to arrange these points in such a way that you cannot partition those points and get that particular graph. Okay? In fact, I'm going to tell you more about this graph. So this graph, no matter what n-gon you give me, no matter, or let's say, how large a set of points in convex position is, you will not be able to partition the points in convex position when they have that particular oriented matroids situation. All the points are in vertices of the point configuration. You will not be able to partition to get this particular graph. But there are some point configurations in which you can partition that and get this graph as a nerve. By the way, you can also play, if you have the intention to play a little bit with your piece of paper, find convex sets that give you this, but not point configurations in convex position. All right? But now, here is another interesting thing. Every tree and every cycle are Tverberg complexes. Okay, so what does that mean? So let me repeat again. That means that there is a constant that is a Tverberg number, so to speak, that gives you, if you have more than that many points, you will be able to realize any tree with n vertices, any graph tree of n vertices. As the nerve of that, it can be partitioned as the points you will be able to partition as a tree like this. Okay? Now, in the plane, we don't know the number exactly. So in the original Tverberg theorem, the constant was very small, very clear, and it's best possible. Here, the constant, we don't know what the constant is. It's much harder to compute, but we know that the constant in the case of the plane is if you have 4n minus 4 choose 2n minus 2 plus 1 points, you will be able to partition those points and get any tree you want in n vertices. Is the theorem clear? Yeah? There's always a partition that gives you any tree that you want. Okay. Here's another part, similar theorem. There's a constant that depends on the dimension and the number of vertices of a cycle. N is the number of vertices of any cycle that you want. And I can find, if I have more than this many points, I will be able to find a partition whose nerve is exactly a cycle. Yeah? And by the way, what I mean by a cycle is really a cycle. There's no, I'm not covering, you know, if I say a cycle like this, I'm not taking the interior, right? It's not, it's just the cycle as a graph, as a one-dimensional simplicial complex. That's important. Is the theorem statement of the theorem clear? Okay, in the case of, here's an interesting thing, because here we really use the classifications of all oriented matrices in a small number of elements. If you have special types of trees, a caterpillar tree is one where you have a path. So a caterpillar tree, you have a path, and then all the other edges are sticking out like this, right? So this looks like a, I guess it looks like a caterpillar. That's why it's called a caterpillar. So caterpillar trees, we know exactly the Tverberg number for those. And it's very similar to the Tverberg number of the complete graph, if you look at it. So here is the theorem. So, but in general, it's pretty darn hard to do, to find the Tverberg number, exact Tverberg number. For example, the fourth cycle, we don't know exactly what the Tverberg number is. It's between 11 points and 13 points. But we don't know and this, the path, the fourth path that I show you, so there you have 9 points is the exact Tverberg number. Because I show you this example with 8 points that you cannot partition, you cannot do a partition that gives you that topology. Okay? So I have about 3 minutes left. So because I would like to talk something about oriented matroids, let me tell you a few things about where oriented matroids come into play. So one essential ingredient where we use oriented matroids is actually to prove our theorems, we needed the multi-dimensional Sekeres theorem. So Erdos and Sekeres proved their theorem for the plane originally. So if you have sufficiently many points in the plane, there's a convex n-gon, k-gon. But it's true in multi-dimensions. If you have a lot of points in dimension D, there will be a cyclic polytope, an alternating uniform oriented matroid in our language, right? If you have a lot of points, you will be able to find a cyclic polytope of any size. And that's one special ingredient we know, because we always reduce every calculation to the case when the points have convex position, essentially. So we prove our theorems in the convex case, and then we need to be sure that the point configuration has some convex polytope inside, and that's how we do it. But to prove this theorem is interesting that you really need to use, so that the proof is essentially a Ramsey-type argument on oriented matrices. You look at the chirotope, you color blue and red the bases that are positive or negative, and that when you have a large chirotope, you will guarantee to have a monochromatic subset that is complete, like a complete graph type of thing, and that guarantees you. So Ramsey-type theorem proves the existence of a multi-dimensional Erdos-Sekeres. Are you with me? Okay, so the other place where oriented matrices come into use is computation. We were heavily computational in this project. So how do we do it? Well, we know that if you have two oriented matroids, or two realizations of the same oriented matroid, they will have the same intersection graph. That's one very useful thing for us. It's not the entire nerve. It's just that one skeleton of the nerve will be the same. And that we use to check whether two, so it's enough because of that to take one representative for each oriented matroid, so we can do a finite search on the spaces of partitions, essentially. And we use the classification, we use the classification of Eisholzer. So Eisholzer had classify all possible oriented matroids up to rank 3, 10 elements. And we use that. We look at one representative for each class of oriented matroids. Then we look at all possible ways to partition, and then we can be sure of who the nerves are in all possibilities. All right, so I think I officially have no time, so let me just end with these open problems. So we still need help to figure out several questions. For example, we don't know the exact Tverberg number for trees. We will be interested to know something about the complexity of deciding whether a particular simplicial complex is Tverberg. That's, I think, a very interesting question. And thank you for your time.
Thank you, Emma. Any questions?
Yes.
Do you know the graphs that are not to Tverberg? No, that cannot be the nerve of any partition. That's what I mean.
So we have this graph that I show here is this one. So this is not to Tverberg.
Yes, but I mean, I said wrongly. But you can find partitions that realize this graph. That you can, you say.
So yeah, so there are some ways to put the points.
Yes.
In such a way that you can partition the points, take the nerve of that, and you get this graph.
Are there graphs
but to be Tverberg, it needs to happen in every point configuration as long as you have sufficiently many points, right? There has to be a value.
My question is, are there graphs that cannot be obtained by any partition of any point sets?
Yeah, thank you for your question. So the answer is yes, and this is coming from graphs that were studied by actually Perelman, the same Perelman that solved the Poincaré problem. So he studied some really weird simplicial complexes that cannot be realized by intersections of convex sets. So this is because our things have to be realized as intersections of convex sets, those graphs will not be of this kind, for example. But they are really more weird in the sense that not even realizable as convex sets.
But they are higher dimensional, or they are graphs?
Yeah, the smallest dimension I know is I think it's the second barycentric subdivision of the 5 simplex. So they are high dimensional. I mean, dimension 5 is the smallest example I know.
Any other question? Okay, so thanks. Thank you very much.